Okay, let's go then. So,
okay, good morning, everyone. My name is Ziad Kopti. I'm the director of the School of Computer Science, professor at the University of Windsor, and former Kayak president. Today, we're here to introduce the talk by Dr. Pascal Poupart. He is giving us a talk about are we experiencing a technological singularity? Very interesting topic. So just a quick bio. Dr. Poupart is a professor in machine learning in the David R. Cheriton School of Computer Science at the University of Waterloo and a Canada CFAR AI chair at the Vector Institute. He also founded the RBC Borealis AI Research Lab in Waterloo, and he is a founding member of the Waterloo AI Institute. He serves as scientific advisor for Huawei's Technologies and Pro Navigator. He received the Bachelor of Science in Mathematics and Computer Science at McGill University in 1998, the MSc in Computer Science at the University of British Columbia in 2000, and the PhD in Computer Science at the University of Toronto. His research focuses on the development of algorithms for machine learning with application to natural language processing, health informatics, computational finance, telecommunication networks, and sports analytics. He is most well known for his contributions to the development of reinforcement learning algorithms. Notable projects that his research team are currently working on include probabilistic deep learning, robust machine learning, data efficient reinforcement learning, conversational agents, machine translation, adaptive satisfiability, sports analytics, and knowledge graphs. He has many awards and many positions and reviewers on a lot of notable papers and conferences such as NIPS and GAIR, ICML, to name a few. So without further ado, I introduce to you Dr. Pascal Poupart with this talk. We will have 45 minutes talk. We will follow with the questions and answers afterwards. So if you have any questions, please type them in the Q&A session in Zoom. Thank you. Go ahead.
Okay, thank you, Ziad. So it's a great pleasure for me to give this talk, and it's a little bit unusual, but it's going to be an interesting experience. Okay, so yeah, I thought I'd ask this question: are we experiencing a technological singularity? In large part because we've just gone through an AI revolution. A lot of things have been changing. We've experienced tremendous progress, and a lot of people are asking questions, where is this all going? So here's the outline of my talk. I'll first define what I mean by technological singularity. And then after this, we'll discuss some of the challenges. In particular, I'll talk about data efficiency and robustness, and I'll tell you a little bit about some of the work that my group has done with respect to those two challenges. So in the form of self-supervised learning and also synergistic methods that combine machine learning and logic. Okay, so if we go back to 1965, Irvin John Good was a mathematician, and then he wrote a very interesting article. It was called Speculations Concerning the First Ultra-Intelligent Machine. And then at some level, he was the first to essentially talk about the singularity. He did not quite use this term, but what he was speculating about at the time is that there might be some artificial superintelligence that will abruptly trigger runaway technological growth. So this was very early on, 1965, but already there were visionaries who thought that AI would eventually change things in a drastic way. If we fast forward to 2005, then Ray Kurzweil, who's a computer scientist, inventor, and futurist at Google, also wrote a book, and the title of his book was The Singularity is Near. So what did he mean in this case? So he was really talking about machine intelligence and humans merging together. And this was based on the observation that when we look at human progress in terms of technology, economy, and so on, we typically have a certain amount of growth. And what typically happens too is that when people make predictions, about what will happen in the future, they look at the past rate and they make a prediction assuming that the future rate of growth is going to be the same. But what has happened instead is that we've noticed over the ages that there's an acceleration, and that comes from the fact that whenever we develop a new technology, then we can use it to essentially develop the next one. So essentially our bootstrapping continuously, and this allows us to really accelerate and to continue to speed up the progress. Now, the obvious question with this is, well, if there's an acceleration, I mean, this has to stop at some point. We can't just accelerate forever because as humans, we are limited. But then his speculation was that, no, this will not happen. There won't be there won't be a flattening of the curve if we want. So here, the growth will continue, and it will continue simply when machine intelligence merges with humans, so that there would be some sort of symbiosis of our technological progress with advances in biology, and then the symbiotic systems will then enable a continuation, and this will be essentially the singularity. Okay, so we're now in 2020. This has not happened yet. What has happened instead? So in recent years, we've experienced a lot of progress, especially coming from machine learning and AI in general. And at least in the field of computer science, we can look at it this way. So traditionally, people wrote program for every task. And when you write a program, you essentially are writing a recipe. You're telling the computer at every step what to do. And here there's a bottleneck, because it means that as a programmer, you have to think about the solution and you have to spell it out. So the computer is essentially limited by what the programmer can think. But then with machine learning, we came up with a new paradigm where instead of simply writing down the instructions, we provide examples to the machine. Right? So here, if we look at tasks in natural language processing, like machine translation or object detection in computer vision, the breakthrough in recent years has been that when you leverage machine learning by providing examples, then the machine can essentially figure out what are effectively the right instructions that it needs to follow in order to do these types of tasks better than anyone could just by programming. So essentially, machine learning provides us a form of meta-programming, because we're not programming the task directly, we're simply programming the machine to program itself. And now you see that enables solutions that are much more complex, much more advanced, and that has led to the breakthroughs that we see today. So then we could define the singularity in terms of self-evolving computer systems. So you see, we've had computer systems that we have been programming for decades and limited by what the programmers could do. But now the systems are essentially programming themselves. So there's a form of self-evolution, and this opens up all kinds of doors. Okay, so now in terms of machine learning, we could say that historically what has been working the best, and still today in the industry, what is the most popular is supervised learning. In that respect, we can think that we have some data that's our inputs. We train a predictor, and then for a specific task, it produces some output. Now, with this framework, the predictor is static in the sense that it's trained to simply map those inputs to outputs, and that's the limit of what it can do. So in terms of self-evolution, clearly supervised learning will not achieve that, or at least will have some limits. So now let me talk about reinforcement learning that opens up even more possibility, or at least the self-evolution here is more natural. And that comes from the fact that we have a system that produces some outputs in the form of actions, but it doesn't end there, because the environment will provide back some feedback. The system will then take another action and so on. And now we have an interactive loop that allows the system to really evolve in ways that had not been thought initially. So self-evolving systems are starting to appear in lots of domains. So for instance, in games, robotics, vehicles, operations research, conversational agents, fintech. So it's becoming more and more pervasive. Okay, so let me illustrate a little bit what I mean by this with some specific examples. So in the case of ComputerGo, if we look at the history, so when AlphaGo was first proposed by DeepMind, then the solution, in fact, combined supervised learning and reinforcement learning. So the first version of AlphaGo was essentially trained by supervised learning to imitate human experts. But obviously, if you want to win and beat human experts, you cannot just train by imitation. You cannot just train based on expert moves. You have to be able to come up with your own strategy, and reinforcement learning became key for that. And some evidence in that respect is that in 2016, when AlphaGo defeated Lee Sedol in 4 matches against 1, there was one match, in particular game 2, where at move 37, AlphaGo made a move that was really unexpected. So in fact, when you watch back some of the videos of the event, the move happened, and then all the commentators were essentially scratching their heads, and they thought, oh my God, this move is not something a human would do. It's probably a mistake. But then everybody started thinking more about this, even Lee Sedol scratching his head, and everybody realized that, maybe this move could have some merit. We're not sure yet. And it turned out that this move was a game changer. And then as a result, it was acknowledged afterwards that this move enabled AlphaGo to win. And it was a move that had never been seen, at least among experts before that. And this was a result of essentially using reinforcement learning to develop a strategy that did not imitate or was not induced by humans. So this is an example here of self-evolution, and that was induced by reinforcement learning. Now, it's not just in games, but if we look at computer networks, so at the moment, telecommunication companies are rolling out 5G networks. The target here is to achieve 20 gigabytes per second, also enable IoT. So that means here we're enabling more capacity, more connectivity. But then those companies are already thinking about the next generation, so 6G networks. An interesting question is, what are they going to be? Right? So what do we mean by 6G networks? Even though this might not be well defined yet, several of those companies are thinking that now this is going to be more an evolution from connectivity to intelligence. So once you've got all that capacity, then you should be able to do some more interesting things. And in particular, they're looking into designing some self-diagnosing networks, self-managing networks, self-evolving networks. And again, part of the technology that is being developed for this relies on reinforcement learning. Okay, another example related to telecom would be smartphones. So if we look again at today's smartphones, when you shop for a smartphone, often you're going to look at the battery life, the camera quality, the resolution, the processor speed, the RAM. So again, I would call that all, hardware features, and mostly, questions of capacity. But then tomorrow's smartphones, or at least a lot of the companies that are developing smartphones, are trying to develop instead adaptive personal assistants and include some apps that would be self-evolving. So instead of being configured based on some questions, they could evolve based on interactions with the user and essentially provide an environment and experience that would be personalized. So again, reinforcement learning becomes key for this. Let me talk about one last example, financial services. So here, especially in Canada, what's interesting is that one of the sectors of the economy that has invested a lot in AI is in fact the financial industry. So it is a strong part of our economy. And if we look at the history of financial services, in the past, what will happen is that you have essentially transactions from A to B, and then the decision to make a transaction would be decided by a human, so some experts, a financial analyst, and so on. At the moment, this has changed, and data-driven services have become popular. And a lot of those decisions now, for instance, who should get a loan and what type of investment should be made and so on, is all based on predictive modeling. But if we look into the future, what a lot of the financial industry is now looking into is to develop adaptive and self-evolving systems, where the idea is that it's not just that we make some predictions, but then those predictions get some feedback, and then you have a system that can evolve and adapt based on the changes. So again, this is something that is becoming pervasive, and then the point of all those examples is that self-evolution is something that is becoming more and more important. Okay, so if we look ahead, in order to enable this type of self-evolution, there are obviously some challenges. So this is not happening completely yet for very good reasons. And I've listed on this slide here 4 important challenges. The first one is data efficiency. So in fact, for reinforcement learning, that is probably by far the most important problem. So it often takes millions of interactions for a reinforcement learning algorithm to find a good policy. And in contrast, humans in the same type of situations might often do this in a few interactions. So there's some questions about how can we reduce that and make those algorithms more amenable to the situations in our everyday lives. So here I'm listing a few techniques that the community is currently designing to improve the data efficiency. And in particular today, I'm going to talk about some work that my group has done with respect to self-supervised learning. So I'll define this in a moment. But the good news is that, yeah, there's a set of techniques here that the community is working on, and we're gradually improving data efficiency. The next problem is robustness. So in this case, again, there are challenges because we develop these really sophisticated techniques that can often break down easily with adversarial examples, or often they're subject to problems in the optimization where they might get stuck into local optima. So again, there's a whole community that is investigating this. And what I'd like to talk about today is one line of work that is combining machine learning techniques with what might be considered more classical forms of AI based on logic, and where together we can achieve a certain amount of robustness. Now, beyond those 2 challenges, there's obviously more challenges to achieve self-evolving systems. We need them to also be open-ended in the type of learning that they do. Explainability is another challenge, but for the purpose of this talk, I'll focus mostly on the first 2 challenges. Okay, so let's dive straight into some examples with reinforcement learning, where I'll tell you about how we can reduce the amount of data needed and also leverage some unsupervised or self-supervised ways of training. Okay, so on this slide, I've got here a very simple type of architecture that is representative of many approaches in deep reinforcement learning. So the goal of deep reinforcement learning is that you have some signal from your environment. So let's say you're playing a video game, so it might be the screenshot of your video game. Then you have a deep neural network, and it could be an actor critique. It doesn't matter really what the architecture is at this point. And what it does is that it produces actions or values. So in other words, it computes a policy, or it might simply compute some Q values. And the idea is that this deep neural network is going to be trained, and it's trained to maximize some rewards. Now, the problem is that in many applications, the rewards are sparse. So what that means is that you might get a reward once in a while. And furthermore, the reward is really a weak signal because it's just one number that you get at every time step if you're lucky. So if we want to speed up reinforcement learning, then we'll need to have some better ways of training. The problem is that here there's an imbalance. So this sparse reward, which is one number once in a while, is responsible for essentially adjusting millions of parameters in a deep neural network. So at some level, it's not surprising if it takes millions of steps, because we have millions of parameters and maybe just one number once in a while. So a better way of doing this that many people in the community have started to investigate is to design some auxiliary objectives. So for instance, if we have an image as input, and obviously we're playing a game, so there's going to be more images in the sequence, then we can design our network to also make a prediction about what the next image is going to be. So if you can predict the next image, then it means you know what's going to happen, and you're more likely to be able to choose a good action. If you can't even do that, then how can you plan and have a good strategy, right? So that seems like you see a basic thing that an agent should be able to do. Now, the benefit of trying to predict the next image is that the next image is itself millions of pixel intensities. So that's a very dense signal. It's a lot more information than just one number once in a while. So now there's hope that we can train a large neural network with millions of parameters in a few iterations as opposed to millions of time steps. Okay, so that's not the only challenge. In any case, what I've explained will help us. We're going to see how we can leverage dense signals. But then there's another aspect as well that's a difference between what humans can do and what computers can achieve. So if you look at this game, for instance, Sequest here, if you've never played this game, that's fine. The point is that when you look at it, you somehow already know what you're looking at, right? So there's a little submarine, there's some swimmers, and then you can usually tell what's the meaning of the different things on the screen. So we already have some prior knowledge about that. So for us as humans, what we see are really moving objects. We can recognize those objects, and we can start reasoning about a strategy immediately. But in contrast, a reinforcement learning agent would essentially see here just a sequence of pixel intensities, so just a big vector of numbers. And imagine if you were being provided with such a vector of numbers, could you play the game as well? No, so the first thing you'd have to do is figure out how to interpret those pixels, and that would be an even bigger task than, in fact, just coming up with a policy. So you see there's some asymmetry between what humans can do and what the computer can do here, and we need to change that. So so here, again, what the computer is really responsible of doing then, because it's fed with pixel intensities, is that this deep neural network really does two things. It does feature extraction to understand and what are the important aspects of an image that it can build a policy on top of, and then it also does policy optimization. Okay, so then the question is it possible to change this in a way that we could have an agent that learns to segment, let's say, the moving objects, and then could start planning directly from this? Okay, so it turns out that there's been a lot of work in computer vision looking at this task. So there's some classic work on supervised segmentation. The problem is that this is labor intensive because somebody has to essentially provide the class for every pixel. But then there's also lots of unsupervised or self-supervised techniques that leverage, for instance, optical flow information. So if you've got cyclists or pedestrians that are moving, then you can measure their optical flow. And that already kind of tells you that, oh, perhaps there's an object here, because if all those pixels are moving in a consistent way, then they might belong to the same object, right? So here, motion is an important cue that we can use to infer positions of objects. So we did some work where we essentially took some previous neural network. There was one called the Structure from Motion Network, or SFMNet. We simplified it to be just for 2D images. And it starts by taking as input 2 images. There's a set of convolutions to extract features. But now from this, we then predict the location of the objects. we predict the motion of the objects and the camera, and then we also compute some object masks that will tell us where's the location. And when we do this, then once we obtain object mass and motion of every object, we can apply this to the first image to reconstruct the second image. And essentially, that gives us a way of verifying whether we have computed a good optical flow. So this is a way of essentially doing unsupervised or self-supervised training to recognize objects, and that can be done quite efficiently. So we applied this in the context of Atari games. So here I'm showing you some screenshots for Breakout and Pong. We feed as input the first 2 frames. So I guess this would be, when I say first 2 frames, I just mean a sequence of 2 frames. And then the network is trained to essentially compute object mask and optical flow. We can see here that it makes some predictions about where the ball is, where the paddle is, and so on. And then it also predicts the type of motion. So here the color indicates a motion in some direction. And you can see that it can get roughly where the moving objects are. And in a game like Breakout or Pong, this turns out to be indeed the most important information to play this game. So we combine that with reinforcement learning, where what we did is we have as a top part here our structure from motion network that essentially infers object location and motion, and that all gets trained based on optical flow. But then this information, we feed it to another part of our architecture that is essentially just a good old actor critique network. So here you can have, as usual, some convolutions that extract some features. But then in top of those raw features, we're going to feed in here the object features and motion features, concatenate this, and feed that to a reinforcement learning agent. Here I'm just putting actor critique to mean that it could be any type of network architecture. So when we did this, we did a comparison with some baselines. So if we take A2C and PPO that are popular baselines, and then we augment them by feeding in the object location and motion, then we managed to improve on 26 games, and here 25 games, while the results were similar for 30 games and 25 games, and then worse for 3 games and 9 games. So let me show you now some examples of how that worked. So I've got 4 games here. On the left side, we see the original view in color. On the right, we see here the object mask as well as the motion of those objects. So this is the recognition that is done by the network in real time, which allows us to inspect what kind of information it's really passing on to the reinforcement learning agent. Now, the beauty is that training this to recognize object motion and location was taking roughly only 1% of the frames compared to obtaining a good policy. So we're able to really do this efficiently, at least with respect to the amount of data. And I'll show you on the next slide how we can obtain good policy with less data. Okay, so the top 3 games here, Pong, Breakout, and Sequest, you can see that it's working quite well. For the game of Beam Rider, this one is interesting because it is doing what it's expected to do in the sense that it detects moving objects, but the moving objects are those beams that are essentially just flowing down the screen. And once in a while, there's some flashes as well. But all of that are just visual effects. They have no bearing on the game whatsoever. What actually matters is this agent here, as well as some of the enemies, and then the missiles that are being shot. But these things are so tiny compared to the beams that are flowing down that they don't get picked up. And then in this case, essentially our approach is capturing objects that are moving, but they're irrelevant for the game. So this is an example where it did not work very well, but we can understand why. Okay, so on this slide, I've got some performance curves that illustrate how well our technique works. So our technique, we called it MOREL, which stands for motion-oriented reinforcement learning. And the technique is in yellow here. In these plots, we're showing the number of time steps that's required to obtain a certain amount of rewards. So the higher and the more to the left a curve is, the better it is. So we can see that for the first 3 games, it's performing quite well, it's improving. But then for Beam Rider, we're essentially feeding in noise because those beams that are flowing down are irrelevant to the game, so it's not helping, and it's not performing better than other techniques. Okay, so this was the first part about data efficiency that I just wanted to illustrate. Now let me switch gears and talk about the second challenge, robustness. So in this case, the problem is that with machine learning, often we can devise some techniques that are quite sophisticated, but they can be fooled easily simply by changing some pixels at random. It's not even visible to the human eye, and the class can change completely. So this is one type of problem when we talk about robustness. But then there's another important type of problem that's more related to the optimization itself. So often machine learning techniques are trained by optimization, and there the optimization is often non-convex. So as a result, we might get stuck into local optima. So in that respect, we don't have any silver bullet to address this. However, if we go back and look at other parts of AI, more classical parts that are based on logic, there are lots of good techniques for doing search, exhaustive search, that can often be used to essentially investigate many local optima and eventually identify the one that's best, which can correspond to the global optima. So what I'd like to do next is to tell you a bit about some work that we've done as well in terms of combining machine learning with more classical techniques based on logic. Okay, so to illustrate this, I'm going to focus on the problem of Boolean satisfiability. So here, I'm assuming everyone's familiar with this, but just as a quick example, this problem is the problem of finding a satisfying assignment of Boolean variables. And we need to satisfy some clauses that can be written in this form. So this problem is NP complete. So it's a good benchmark in a sense to see how well machine learning techniques could do in terms of finding the optimal solution or the exact solution. Okay, so what are the classic techniques, or maybe not so classic, but I guess modern techniques for doing satisfiability? So today, modern SAT solvers are essentially of the type known as conflict-driven clause learning. So those solvers take a SAT instance, they quickly propagate values to variables for which there's no choice really. And then after that, what they start doing is to assign some variables by branching, okay? So the way the algorithm operates is that you start with some variable and then you might try a true or false. So you're branching essentially on that variable. Then after that, you assign another variable. You try again with true and false, and you're doing a search in this fashion. So these techniques effectively do a search. It's an exhaustive search, but the idea is that they cut off this search in smart ways. And one aspect that makes these techniques quite effective is that whenever they reach a dead end and there's a conflict, they'll do some analysis and often produce a new clause that can be added, and this new clause will help to speed up the search afterwards. So that's why they're called conflict-driven clause learning, and pretty much all the modern SAT solvers today are based on that. Okay, so one issue with I guess these techniques here is that there are often heuristic decisions in terms of how to design or how to make decisions at different point in time in the algorithm. And one important decision that I've highlighted here in red is in terms of branching. So what variable should we branch on next? And if you branch on good variables, you can make your search quite efficient. If you branch on variables that are not so good, it might take a really long time. So that's a key part of the algorithm. How do you branch? And historically, the heuristics for branching were all designed by hand based on trial and error. And there's an interesting question about can we do better? And here, this is where there's an opportunity to combine this with machine learning. So the choice of branching can be thought as some form of classification problem or some form of prediction problem. And the idea is that instead of designing a heuristic by hand that might or might not work, why don't we do something that's data-driven that will learn automatically from its experience? So what we did is we designed an algorithm that effectively does learning to branch. And here, there's a tendency in machine learning often to go for heavy models, but in the context of SAT, we need something that's efficient. So what we did is we designed an algorithm that's very simple based on a multi-arm bandit, which is just a special case of reinforcement learning. So here what we did is we modeled the choice of variables. Well, so actions are essentially the choice of variables. And then to see how good are those choices, we have a reward that corresponds to what is known as the learning rate. So here the learning rate is the rate at which new clauses are going to be obtained during conflict analysis each time that a dead end is reached. So more specifically, we can define the learning rate essentially being the number of learned clauses that involve a variable v in some time interval I divided by the total number of learned clauses in that same interval. So here, the more clauses are learned when we choose a variable, then the faster our search is going to perform, and that's a good thing. So we formulated the problem as a multi-arm bandit in this fashion. And then in terms of algorithm for multi-arm bandit, we just use a simple technique that's essentially an exponential moving average. So here you'd like to choose the arm that has the highest reward over time. But because in this problem, things are non-stationary, so what you learned in the past might not necessarily be reflective of the current situation or the future. So it's important to, in fact, discount some of the really old past experience. So that's why we use an exponential moving average. Okay, so we use that, and then we tested that as part of the mini-SAT solver, which is a common framework for testing a lot of ideas in SAT. And this plot here shows how our heuristic based on this multi-arm bandit, we call it LRB, so learning rate branching, it performed the best. So you can see on this curve, so we'd like to solve as many instances as possible in as less time as possible. So here we want to have a curve that is as far as possible on the right and as low as possible. Okay, so then our approach improved compared to previous branching technique. And in fact, when we incorporated that into the Maple SAT solver that was entered in the SAT 2016 and SAT 2017 competition, ended up winning in some of the tracks a gold medal, and in 2017 also a silver medal. Okay, so now this was just a simple thing where we changed one way of one decision in the whole CDCL framework. But a question could be, well, what if we try to do machine learning to solve the entire problem and not rely on existing techniques? So here I'm going to call that learning to satisfy. And we can indeed formulate the satisfiability problem as a learning problem. And this will also expose quite obviously any issues of robustness, because it might get stuck into local optima. It might not find the optimal solution if it's not robust. Okay, so one way of doing this is that we can formulate the problem by saying, let's have a variable that tells us the probability with which we could assign that variable to true. Okay, so ultimately for satisfiability, we come up with an assignment of all the variables. We don't know what's a good assignment, so we're simply going to have a random variable, and then the process of learning is going to essentially try to figure out what is a good value for each theta. Now, we have clauses, and in this framework, we're going to think of the clauses as essentially data for a machine learning problem. So if we have a clause that is, let's say, V1 or V2 or not V3, then we can define a conditional probability that this clause is true given specific values for θ1, θ2, and θ3, and it would be equal to this expression. Okay, so this gives us the probability with which the clause would be satisfied if, depending on what's the probability that each variable is true. Okay. So now with this, we can formulate satisfiability as a Bayesian learning problem, where we can start with a prior. So we don't know what the thetas are. So we're going to have, let's say, a product of beta distributions over those variables. Then we can take our clauses as data, compute a posterior. So now we'll have the probability of the thetas given the clauses. And the idea is that if we look at what is this best theta, or if we simply do the full Bayesian learning and really look at the full posterior, then there are ways in which we could recover a satisfying assignment if there exists one, and if there doesn't exist one, there are ways as well to tell that it's impossible to satisfy this. Okay, so we can formulate satisfiability in this fashion. The only problem is that when we compute our posterior, we'll end up with an exponentially large mixtures of beta products. So at some level, this is not surprising, because if we did that in a tractable fashion, we would have shown that P equals NP. Okay, so it's normal that there's some intractability. So in that respect, machine learning techniques or the machine learning field usually does not shy away when there's intractability. We approximate, and then we see what happens based on that. So in this work, we considered one way of approximating, known as Bayesian moment matching. So we take our prior, which is a beta product. Whenever we observe a clause, we do an exact Bayesian update, and that would normally give us a mixture of beta products. But instead of letting that mixture grow and become exponentially large, after each clause, we simply project by doing what we call moment matching. So here what that means is that we take our distribution, which is large, and then we map it down into a form that is simpler, just a single beta product, by ensuring that the moments of those two distributions match, at least for the marginal mean and the marginal variance. The other moments will change, so that's where there's an approximation, but at least these are going to remain the same. Okay, so now that gives us an algorithm that's going to be tractable. And now the question is, what happens to robustness in that respect? So as you might expect, here exact Bayesian learning, as I mentioned, will allow us to solve the satisfiability problem exactly, so find an optimal solution, but it's intractable. Bayesian moment matching that I just discussed is tractable. So this algorithm with the moment matching projection, in fact, gives us an algorithm that scales linearly. So it's beautiful, but naturally, it's not going to give us the optimal solution all the time. So it's really something approximate. But when we looked at it empirically, we noticed that this Bayesian moment matching technique on many benchmarks was capable of satisfying 90% of the clauses in less than 1 second. So it's like really close to having a complete assignment when there exists one, but it's not always accurate. So one idea then is, could we simply combine this Bayesian moment matching technique with a modern CDCL solver? And perhaps we could do this simply by initializing the solution in the CDCL solver with the Bayesian moment matching solution, and then let the CDCL solver do an exhaustive search after that to really find a satisfying solution if there exists one, or otherwise prove that there doesn't exist one. And then the benefit of doing this is that now we can get both optimality that comes from the CDCL solver, and then improved tractability that comes from this fast initialization. Okay, so when we did this, we first compared how different solvers, so we took 3 different CDCL solver. One of them is called CryptoMinisat, another one is Glucose, another one is MapleSat, and then we compared each one of them with a version of itself that uses Bayesian moment matching to initialize the solution. And so, for instance, here, if we look at the open square versus the filled up square, then we can see that the curve for open square is higher than the one for filled up square. So that means we're improving. So here again, these are cactus plots where we want to have a curve that is as low as possible and as far to the right as possible. If we compare glucose with and without Bayesian moment matching, then same idea. So we can see that it improves. And then for cryptominisat with and without Bayesian moment matching, it also improves. We tested this on the SAT 2018 benchmarks, where we took this the state-of-the-art solver for that benchmark, Maple Comps, and then initialize the solution with Bayesian moment matching. And now we compare that to different ways of initializing as well. And then it led to the best results here. So I guess what this shows is that we now have a way of combining these things where we can benefit from the improved accuracy from Bayesian moment matching, and then the optimality that comes from the CDCL solver. Okay, so I'm going to stop here and simply conclude my talk. So what I've presented is essentially, first, we had a discussion of this notion of singularity. So in the past, there were several definitions about what that might mean. What I'm suggesting is that we might be experiencing some singularity, but it would be more in terms of self-evolving systems. At least machine learning has enabled adaptivity. And now with reinforcement learning, this adaptivity can be taken to another level. And this will lead to more progress, acceleration, all kinds of new services. And this is pretty exciting. But then to achieve that, there are some challenges. The two that I talked about are data efficiency and robustness. And here I'm just showing you what are the references of the work that I presented. So feel free to have a look at that, and you can also ask me some questions afterwards. But essentially, two directions that I think are quite promising that I just illustrated with some of the work that my group has done are self-supervised learning and also synergistic ways of combining machine learning and logic. Now, you might ask still, will there be a singularity? How close is it? And obviously, I don't know, but there's only one thing that I know for sure, is that with all the advances that we see in our field, there's going to be some gradually more adaptive and autonomous systems. Okay, so let me stop here, and I'll be happy to take some questions.
Thank you, Dr. Poupart. This is a very interesting talk. Bit scary, though, to think about where we're going with the singularity and how much the computers can do today. A lot of people ask about the power of AI, and very curious to see some of the future work that's just going to come out of this as it's still in its infancy here, but it's accomplished a lot. So just a word for the audience, if you like to submit your questions, you have a few ways to do so. You can type them in the Q&A chat. You can type them in the Slack, which might be a little bit slower because they have to be copied over to us. You can also raise your hand, good old fashioned raise hand, but not in the video. Do not raise your hand in the video because we don't see you. But if you go in the participants in the Zoom, there's a raise hand function that you can click, and I should be able to see your hand raised and call you out to speak. Just remember to unmute your mic when you ask your questions. So I'm going to open the floor to the questions. Go ahead. So I guess while people are getting set up, if I can ask in a game of Go, so when the computer did this odd move, was it really like the significance of this move? Was it really thought by people that this would be just a mistake, as a possibility to make mistakes, or is it it wasn't like, did they know right away it would be a mistake? When you said no human would have made that move, can you elaborate on that? Like, what would that be?
Okay, so I'm not a Go expert, but there is a nice documentary that I saw on Netflix that was produced by DeepMind, where they essentially show, I guess, what happened when that move took place. And there were commentaries done in English by some Go experts and also in Korean by other Go experts. And then there was also the team at DeepMind that was working on, well, that was just watching their program play. And essentially those three groups of people, according to the documentary, all initially thought that this was a mistake from the computer. Okay, so because it was just not a move that experts would do. So like the commentaries from the experts, both in English and Korean, were the same, that this must be a mistake. When DeepMind saw this move, the developers were pulling their hair and thought, oh my God, our computer program also just screwed up, okay? And later on, at least according to the documentary, then as time was passing by, everybody was, starting to think, okay, would it be possible that maybe this is not a mistake, and perhaps it was a smart move. And then, I mean, with the rest of the game, what was observed is that this move led to a key advantage, and indeed it allowed AlphaGo to win.
Thank you. This is interesting. So I have a question here from Chris Dumont. Chris asks, much of current research is in designing network structures. Is that the most promising direction? And a follow-up, what about more general techniques such as naive physics or learning more general knowledge?
Okay, so yeah, the designing network structures, I think at least learning to obtain network structures automatically, I think is a very important research direction. And it is indeed a bottleneck for the industry. So in fact, there's an expression at this point where people say that what is being done is graduate student descent, in the sense that it's the grad students or otherwise the developers that are essentially just doing trial and error to find some good architectures. And often this is the result of what I would call a lack of robustness on the optimization side. So sometimes it's not even clear that one architecture should be better than another one, at least at the highest level. It's not clear, but then we're doing non-convex optimization. In some cases, we could prove that there exists a good solution with both architectures, but then in practice, somehow our optimization techniques tend to find a good solution more easily with some architectures, but not others. So it's really, really difficult then to obtain good architectures. And as a result, there's this entire field now of architecture search or structure learning. And I think this is very important, but it's actually closely related to the problem of robustness that I was talking about earlier. So I think that if we can at least mitigate that problem, this will definitely open up a lot of possibilities and free our grad students and also many developers in companies.
Okay, thank you. And I forgot to mention that apparently in the webinars, people cannot unmute themselves or speak up. So you'll have to type your questions in the question and answers box that you will see. So we have a question from Leila Hussein. First, she thanks you for a great talk. And she says, can you give us your thoughts on other areas of research, whether in AI or others, that will benefit from reinforcement learning in the short or medium terms?
Okay, yes. Okay, one other area that is dear to my heart and probably to Leila's heart too is natural language processing. So there has been, in fact, a history of work in dialogue systems that use reinforcement learning. Now with modern conversational agents that are trained often with sequence-to-sequence models, and you can often do some fine-tuning with reinforcement learning. But where I think there's some really nice opportunities is that we might want to change how we do the training. So instead of having pairs of message and responses that are used to train to essentially imitate, if we take a conversation in the same way that we as humans can essentially learn directly from a conversation, so we can pick up cues that when we say something, whether the other person we're talking with understands us or does not, right? Then we can essentially revise what we're saying, what our understanding is, and so on. So this is where I would think that reinforcement learning should be able to unlock new ways of doing some online learning of within conversations. And I haven't seen a lot of work do this or even achieve that. But ultimately, that could also reduce the amount of data that's needed, because if you can deploy something that simply learns as it interacts, then this will be a new paradigm. And I think there will be lots of possibilities.
Okay, thank you. There's a bit more general question from probably one of the students asking whether the code of any of the work that you have provided is available. Perhaps there's any public domain repositories, so for somebody to get started. And well, also a follow-up, if you could, kind of point students out, if for the students audio in the audience, the new MSc students looking into doing research in this area, where could they get started? Are there some good starting points that you would
Okay,
recommend?
so yeah, this is great. And so, okay, with respect to the work on reinforcement learning, if people go to my web page, you can simply type my name in Google. You'll find my web page as the first hit, and then you go under my publications. You'll see this work here on self-supervised learning. So this particular paper on unsupervised video object segmentation for deep reinforcement learning, and then the code is also published. So there's a GitHub repository. You can download this, try it, and extend that if you want. For the work on SAT, so here, my colleagues at the University of Waterloo, so under Vijay Ganesh's direction, I believe have also published their code. So in fact, this work was the basis for the Maple SAT solver, and it has been used by other people and extended. So this paper from 2016, then the code is available. For the second paper, this is something that is currently under review. We should find out, so it's under review with ICML. We'll find out in a few days if it's accepted, and there too we will be releasing the code as well. So here, it's Mr. Nejati who wrote most of the code, and I'm pretty sure we'll be releasing it. So yeah, so the code for this work is available. If people want to get started with some of these things, in a case of reinforcement learning, people should feel free to go to my webpage. I taught a course in 2018 where I recorded every lecture. So it was a graduate course on reinforcement learning, but we start from zero and then we go to fairly advanced techniques. And then every lecture was recorded. So there are video lectures that people can watch. Now, as we speak, I am teaching again a course on reinforcement learning. And because of COVID-19, we have no choice. It's an online course. So again, I'm putting videos online for this. And it's happening right now. I just started this week. It's continuing till the end of the summer. So people should just feel free to go and watch the video. So everything is on my website again. So the course is CS885. And I guess beyond that, many people in the community are also now putting material online. So this is a great time to learn. And I would encourage everyone to just do a bit of search, and you'll find lots of good resources.
Thank you. This is very informative. Certainly, it's a wonderful talk. And on behalf of the audience present and on behalf of the panelists, Dr. Pascal Poupart, we thank you for your time today. This is a very eye-opening talk, and certainly a lot of useful information for the students. you know, a lot of people are tempted now to register in your course. Hopefully we can see and learn about more about your work, and hopefully we continue to see some of the results, and hopefully hear back positively from the ICML. Okay, thank you again, and thank you, the audience, and I'll pass it on to Cyril.
Yes, thank you, Ziad. So let me take back the mic for a couple minutes. So first, I wanted to thank Pascal for this great talk, and thank the audience for attending and for asking some questions. I wanted to say that usually we would be, at the end of this keynote, we would be sharing the same podium on a physical conference, and we would give you a small gift of appreciation, but this is a virtual thing. So Kayak wanted to thank you, and you will get this by email instead. You know, these are new times. So thanks again, Pascal, and also to follow up on what you just said, we have a tutorial on reinforcement learning that will be given this afternoon, starting 1:30 Eastern Time, given by Pierre-Luc Bacon from Université de Montréal. So it is in a different room. The information is on the web and on Slack, and hopefully the live stream will work from the start this time. So thank you. Xiaodan, did you want to add something?
No, not for me, but thank you very much, Pascal. Thank you very much, Ziad, and thank you, everyone. So again, so this is first time we moved to online, so we still try to experiment more things. And thank you very much again. See you later.
Thank you all for this first session, and see you in another meeting room.
Okay, thank you.
Bye-bye.
Bye-bye.
Thank you, Pascal, very much.